Now, generally, there are two types of chemical reactions. You've got endothermic reactions and you've got an exothermic reaction. An endothermic reaction is a chemical reaction that must absorb energy to continue. Because of this, these reactions cannot occur spontaneously because they need heat. And what you will experience is a temperature drop due to the reaction absorbing heat from its surroundings. Now, these are not generally considered an issue in relation to fire safety because generally they're not self-sustaining and they do not result in a fire. So they're generally not concerned because fire is not an endothermic reaction. Now, an example actually of an endothermic reaction is when acetylene cylinders are heated in a fire. When they're heated, the cylinder will absorb the heat and this causes an endothermic decomposition of the acetylene. Now, what this does is it makes the cylinder unstable and that cylinder could explode if it was susceptible to a shock, for example, if it was knocked over. This is why the fire brigade deal with incidents so severely and they attend hundreds of incidents every year involving acetylene. Now, when I was in the fire brigade, if we turned up to an acetylene cylinder involved in fire, first of all, we'd extinguish the fire, we were going to cool the cylinder, we'd get a thermal imaging camera out, make sure the cylinder's cool. When we're happy that it's cold, we would create a dam, put pipe, fill a dam with water, and we used to manhandle the acetylene cylinder inside the dam, and we would leave it there for a minimum of 24 hours, and then we'd get a company to come and dispose of it. That's what we used to do when I was in the fire brigade. Now, the fire brigades don't even do that. They don't touch them. What they do is they put the fire out, they cool the cylinder, and when it's totally cool, they leave it for 24 hours. They do not move it, and they get companies in to move them afterwards. There was an incident on the A14, and a vehicle was involved in fire, and it had acetylene in the back. And basically, the fire officer of attendance did not know if that cylinder had been susceptible to shock. In other words, the endothermic reaction started. So he had to treat it as though the cylinder had been heated. They extinguished the fire, and once they'd extinguished the fire and cooled it, he said, we're going to have to leave for 24 hours. It was right now on the A14. They had to close the A14 for 24 hours. And it caused uproar. Everyone's mourning, saying, no, you can't close the A14. He had no choice, because if he hadn't closed the A14 and he'd left that cylinder and the vehicle had gone past and it had been susceptible to shock and somebody died, the fire officer would have been at, why did you not close the A14? So we had no choice. Generally, in the UK, we have a passive approach to dealing with the acetylene cylinder involved in fire. We cool them and we leave them for 24 hours. That's the safest way. What do other countries do? Some countries, they actually shoot them. They've got a high-powered rifle and they shoot the acetylene cylinder, and it's got a phosphorus tip. So as it goes through the cylinder, it hits the cylinder. When a bullet stops at a cylinder, what happens to the bullet? Well, all that kinetic energy of that bullet turns into heat energy and the bullet melts. But as it manages to go through the side of the cylinder, and the phosphorus tip creates a spark. Now what do you get? Well, it starts to burn off. You get a flame given off. Now you shoot this cylinder 3 times, you've got 3 flames coming out of the cylinder. What is that doing to the cylinder? Well, it's making it safe. Now, once that gas has been burnt off, what is it? It's a lump of metal. And I know some of the fire officers went to this country to look at their methods and to see if they were going to adopt them over here. They looked at all the different ways they do it, you know, the training and everything. When they came back, they decided, actually, we'll stick with what we do. We do a more passive approach, some of us do active approach. Now, what is an exothermic reaction? Well, an exothermic reaction will give off energy in the form of heat, light or sound, and critically, it gives off more heat than is required to start the reaction in the first place. So it's classified as self-sustaining. Now, these reactions can occur spontaneously. For example, in a haystack, spontaneous combustion of a haystack. Quite a lot of fires were caused by this, because at the time they didn't realise it's about the critical size of the haystack. If you've got a barn and it's completely filled with hay, oxygen will get in and there is a reaction going on in the straw with the conditions. And if it's right in the centre, it'll start to heat up and it starts to spread out. Now, when that reaches the outside and the oxygen, if it's over a critical size, you could experience spontaneous combustion. Now what they do with the barn, they break it down. They have hay, they have the bales of hay, but they leave an air gap between them, so many. And the idea of that is not to exceed the critical size, to stop spontaneous combustion. Now, exothermic reactions can cause serious fires and explosions in the workplace. Now, if a chemical reaction is heated, involved in a fire, that chemical reaction process actually accelerates. No, if you increase the temperature of a chemical reaction by as little as 10 degrees, it doubles the rate of the chemical reaction. Now, following on from this, I'm now going to look at the nature of fire. Fire is an exothermic, so we just cover that, a heat-releasing chemical reaction between a fuel and oxygen. And for combustion to exist, there are three elements required, and this is generally referred to as the triangle of combustion. So what do we need to have a fire then? We need fuel, we need a heat source, and we need oxygen or an oxidizing agent. In its simplest form, we always say oxygen. However, it could be an oxidizing agent. Now, some oxidizing agents contain oxygen. For example, nitrates, chlorates, they generally will contain oxygen in their structure, like fertilizers. They actually have oxygen in there, and when they're heated, they release oxygen and then become dangerous in a fire. However, not all oxidizing agents contain oxygen. Fluorine, rocket fuel, hydrogen fluoride is rocket fuel. Where's the oxygen? There isn't any. It doesn't have to be oxygen to burn. It can be an oxidizing agent. Another one is chlorine. If I got a bag now, a plastic bag, I put hydrogen gas in, put some chlorine in there, gas, and I seal the bag up and put it out on a sunny day, which is very rare in the UK. You put it out there on a very sunny day, what will happen is that will react and it will bang, bang, and you will get a drop of hydrochloric acid on the floor. What you have seen is an oxidizing process. The hydrogen and chloride have combined. So oxygen or an oxidizing agent. So how do you extinguish a fire? Well, if you remove any of these elements, the fire goes out. There are actually 4 ways to extinguish a fire. 4 ways. One of them is smother. You can displace the oxygen. You can cool it, which removes the heat. Or you can starve it, in other words, remove the fuel, remove what's burning. Or you can, chemical reaction, you can interrupt the chain reaction, because combustion is classified as a chain reaction. You can interrupt that. Well, we're going to move on to that now. Well, that's the basics. Let's now cover the combustion process. What actually is fire? Combustion is a vapour phase reaction. What does that mean? For combustion to occur, the molecules must be in the gaseous phase. The solids do not burn. Liquids do not burn. Only gases are capable of combustion. If you get a piece of wood and heat it up, what you'll find is pyrolysis will start, and basically the solid will turn from a solid to a liquid to a gas. It gives off gases. In other words, when you see a flame coming off a bit of wood, what you're not actually realising is it's the gases that are burning, not the solid. It's giving off gases. That's why you aim the water at the base of the fire, to stop the gases being given off. It's got to be a gas. Let's look at the simplest form of combustion. This is combustion of pure hydrogen. 2H2 plus O2 give you 2H2O. That's the simplest form of combustion. That's what it's saying is, if you've got 2 molecules of hydrogen and you combine them and they get a chemical reaction with 1 mole of oxygen, in other words, put an ignition source in, you will get 2 molecules of water. That is the simplest form of combustion. That is the burning of hydrogen. But what does this actually mean? Well, let's explain it. I've got 1 molecule of hydrogen, and H2, have you noticed it's always H2O2N2? And that is because there's no such thing as a hydrogen atom flying around. It's got to be in molecular form, and a molecule of hydrogen contains 2 atoms of hydrogen with a bond between them. It's like holding hands. And they haven't got strong bonds, they've got a bond. Now, hydrogen is a flammable gas. Now, those bonds actually aren't very strong, but they've got a bond. What happens if you put an ignition source in the air with hydrogen? Well, if you put an ignition source, what happens is that ignition source breaks the bond. So now, from one molecule of hydrogen, you have now got two atoms of hydrogen, which are called radicals. When you see a little star next to it, that is a radical. Now, these radicals have got high energy, and they cannot exist independently for a long period of time. In other words, they can't stay like that. They've got to combine with other molecules. They've got to. So what happens is you burn hydrogen, you get radicals. What do? Well, they fly around in the air and they can bump into other molecules. What might one of these bump into? Well, it could bump into an oxygen molecule. Well, what's an oxygen molecule? Well, it's O2. Two oxygen atoms combined by a bond, holding hands. Now, this oxygen molecule is minding its own business, flying around, and this hydrogen radical, which has got high energy, smashes into it and it breaks the bond. And what it does, when it breaks the bond, it combines with one of them. And what you'll find is you'll get this. You'll get an OH hydroxyl radical and an oxygen radical. This is why it's the chain. From what you started with, one molecule of hydrogen, you've got two radicals, now you've got three. Do you see what's happening when you get combustion? You're recreating, you're moving some type of molecule, you're combining it with oxygen to make other molecules, and that is what combustion is. Now, these radicals cannot exist independently, so now these radicals fly. If you've got an OH flying around, you've got an oxygen radical flying around, what could happen now? Well, the hydroxyl radical might bump into, which it eventually will do, a hydrogen molecule. When it does, it breaks the hydrogen molecule and it combines to form H2O. What is H2O? Well, it's a molecule of water, which is very stable. When it combines to form H2O, what happens is this has got a very, very strong bond. And if any other radical bumps into this molecule now, it's not interested. It doesn't break. It's got a very, very strong bond. So that's why, if it bumps into it, it just bounces off. And when it combines to form H2O, any excess energy that all these radicals have, they dump. They give the energy away. And what does that molecule and that energy do? Well, it starts the next process off. In other words, the radical chain process. When you set fire to anything, a gas or anything, and you see an explosion, what you don't see is millions of these reactions happening at the same time. And what's happening is unstable molecules are forming stable molecules by this process. That is the combustion process. Now let's move on to see how the oxygen concentration can affect these reactions then. The availability of a sufficient supply of oxygen will seriously affect the fire growth rate. In other words, increased oxygen will result in a faster fire growth rate and experiencing higher temperatures. If it's well ventilated, it can lead to a phenomenon called flashover, which I will cover later on in the element. Now, if you increase the concentration of oxygen, this will increase the risk of fire, and substances which would not normally be considered hazardous will now burn. And the reason is because you're getting closer to what we call the stoichiometric mix, which is the perfect mixture for combustion to occur. What can affect the availability of oxygen then? Well, you've got ventilation systems, air conditioning, windows breaking, doors open, anything that lets oxygen circulate around a building. And that's why in a fire, these systems should be closing. So ventilation systems and air conditioning systems, when the alarm goes off, should actually be shut down to stop this oxygen pumping around the building. Now, many accidents occur in an oxygen-enriched atmosphere. I mean, one in the care industry. A carer went to a home and there's a gentleman having oxygen therapy. He's having oxygen therapy mask. Psh, at the same time, he's having a cigarette. He's having a... Psh. First of all, what's the point? What's the point of that? And fire hazard. What would have happened if he'd have decided, I'll have another fag. He lights it up next to the oxygen. That match gets that oxygen near it. What would have happened? Bang. And there was a case in Scotland where somebody was killed because they were smoking at the same time as they're having oxygen therapy. Now, oil and grease are also particularly hazardous with pure oxygen. You never put oil or grease anywhere near an oxygen cylinder valve. If you put grease or oil on an oxygen cylinder valve and pure oxygen gets near that, you will have rapid oxidation and you will have combustion. Spontaneous combustion. We're at that again. What does this mean then? Well, this is the stoichiometric. This is a perfect mix. 2 molecules of hydrogen with 1 molecule of oxygen will give you 2 molecules of water when combustion occurs. Now, that's the perfect mix, but that doesn't happen. We're not living in pure oxygen, are we? We're living in air. And what's air made up of? Well, about 20% oxygen, 79% nitrogen and other gases. In other words, this is actually the combustion of hydrogen in air. You've got 2H2 plus O2 plus 4N2 give you 2 molecules of water and nitrogen. That's what combustion in air is. Now, what does the nitrogen do in that reaction? Nothing. However, it takes away energy from the reaction, but it doesn't take part. It gives nothing back. Why? Because molecules of nitrogen are inert. And an inert gas has got very, very strong bonds. In other words, it's not going to smash if a radical bumps into it. It's got a very, very strong bond. So while all these reactions are occurring, all the heat's been applied, and it's all heating up and expanding due to convection, the nitrogen is acting as what we call a thermal load. In other words, it's actually been involved in the chemical reaction, but it's not taking part and it's not giving anything back. It's acting as a thermal load. In other words, that's why you carry out oxyacetylene welding. You will get a hotter flame temperature. If you burn acetylene in air, you might get 1,000 degrees because a lot of it's been wasted on the nitrogen. If you burn it in pure oxygen, you get 2,000 to 3,000 degrees. That's why oxyacetylene welding is carried out.